Physics errors. The concept of motion. Motion, what it is like, everyone can see. In fact, there doesn't seem to be anything to discuss here. Everything around us moves, that is, it changes its position in relation to time. Waves, cars, people, animals, everything is in constant motion. The common feature of this motion is that we are able to observe the motion continuously, and we define it by the speed defined as v equals ds by dt. All bodies move in such a way that we can accurately determine all points in space that a given object has traveled through in motion, i.e., the bodies do not jump immediately from point A to point B, and the path traveled by these objects can be represented as a continuous line. At the same time, even the greatest accelerations are smooth. That means there are no instantaneous changes in speed. The speed is always changing smoothly, even at the strongest accelerations. In other words, the speed that determines the objects around us is differentiable at all points on the object's path. We see such a world around us, and we are used to this image of the world. At the same time, the speeds we deal with on a daily basis are non-relativistic speeds, i.e. much lower than the speed of light. So the world that surrounds us is non-relativistic, which in practice means that the image of space-time we see every day corresponds to the true image of this space-time. No wonder that when creating models of reality, we try to make these models similar to the world seen around us. However, the problem of motion is much more complex than we think. This was leading to errors in the past and has also caused considerable errors today, causing the unnecessarily complicated model of reality currently in force in science. First error: choosing a non-proper reference system. For example, if we consider the motion of a car, it can be represented in two ways. From the point of view of an observer standing on the roadside, and from the point of view of the car's passenger. Thus, theoretically, we can consider the motion as relative. However, the description of the car's motion from the point of view of an observer standing on the side of the road is relatively simple. We have car's coordinates and only they change. From the point of view of mathematics, we can also describe the problem the other way around. We can assume that the car is stationary and the whole world is moving around the car. Such a description requires a description of the motion of all the elements surrounding the car: roads, trees, poles by the road, etc. Such a mathematical description is correct, but is much more complicated than the description of the same problem from the point of view of an observer on the roadside. In addition, passengers feel the effects of the car's motion. They feel braking, acceleration, change of direction of motion. Thus, the problem of whether the car is moving or the entire environment is easy to solve due to the very large number of points of reference and the perception of the effects of the movement by the car's passengers. However, such a problem in interstellar space is no longer so obvious. We have much fewer landmarks, and in addition, we do not feel the effects of the movement as the car's passengers do. The problem of treating the relativity of motion, as in the case of a car, requires choosing a frame of reference. We can choose a system related to the Earth, and also we can choose a reference frame related to the Sun. If we stand on the side of the road and observe the motion of the car and the motion of the Sun in the sky, we see that both the Sun and the car move in relation to us practically the same way. Well, maybe the Sun does not accelerate and brake and turns more gently. Thus, taking advantage of the similarity of the motion of objects on Earth and the motion of heavenly bodies, Ptolemy, around AD 150, created a description of the universe, assuming that the Earth was at the center of the universe, and the Sun moves around the Earth just like all other things move around us. We know now that this is not true, but almost 2000 years ago we were only discovering the shape of the universe. Returning to our analogy with the car, the description proposed by Ptolemy corresponded to the description of what passengers see from the windows of the car, assuming that it is not the car that is moving, but that the whole world moves outside the window. However, this world seen from the car, which is the Earth, is much simpler than the landscape outside the window and consists of only four groups: the Sun, Moon, planets, divided into outer and inner, and fixed stars. The mathematical description of such a universe was complicated. It was necessary to introduce non-intuitive epicycles, equants, and deferents, but the description worked, and for 1500 years it was considered as a brilliant mathematical work of scientists. It was not until the mid-16th century that Copernicus published a work in which he revived an abandoned ancient concept of a world in which planets revolved around the Sun. Perhaps that this concept was inspired by the central role of the Sun in antiquity, where the Sun was a god. However, for about 100 years, Copernicus's theory was treated as a curiosity without proof, and therefore ignored by the Inquisition. Only the observation of the motions of Jupiter's moons made by Galileo in the 17th century gave a very large argument for the truth of Copernicus's hypothesis, and this curiosity became a scientific theory which was already a thorn in the eye of the Inquisition. But interestingly, the predicted displacement of the fixed stars due to the orbital motion of the Earth around the Sun was only confirmed in the 19th century, because only then sufficiently accurate optical instruments were developed. In this context, the rehabilitation of Galileo in the 20th century does not seem as grotesque as it was presented in the press. It's just that the church mills grind slowly. So, we have the first brilliant but flawed theory in the history of science. Ptolemy's theory is a thing of the past. But is this the end of the wondering of science? Second error: bodies or waves? Maybe we'll start with the types of motion. I would like to mention the motion of bodies and the motion of waves. Here we limit ourselves to uniform motions with constant speed. Bodies. We observe bodies as objects in empty space. The motion of these bodies is a change in the position of the body in relation to another body. We generally treat motion as relative motion. Bodies can move in empty space where there are no points of reference. In such an empty space, we are not able to determine whether the body is moving or is at rest. In order to determine the motion, we must therefore determine the point relative to which the body is moving. If we only have two bodies in empty space, for example A and B, then we can assume that body A moves in relation to body B, or vice versa, i.e. that body B moves in relation to body A. Waves. Waves. We have a different case here. The wave needs a medium for propagation. Waves propagate through air, water and solids. The common feature of waves is the necessity for existence of a medium, while the speed of wave propagation depends on the properties of the medium. So, waves and bodies have completely different properties. However, over time it turned out that under certain conditions bodies show a wave structure and waves can behave like bodies. In addition, electromagnetic waves do not need any medium to propagate, and they propagate at a constant speed, but not in relation to empty space, but in relation to bodies. And the speed of propagation of these waves is the same in the system of any body, regardless of the velocity of this body. And in order not to be too easy, it turned out that at very small distances we are not able to accurately determine the position and momentum of the body, but only the probability of finding the body at a given point. So there were a lot of complications over time, which were nevertheless managed to be mathematically described. The constant speed of light was solved by adding the equation of conservation of the space-time interval. The wave properties of bodies were described by quantum mechanics using the abstract wave function, which is a more general form of writing the equation of an ordinary wave, and here it has a meaning of the probability of finding a particle at a given point. The equation describing the particle states for very small distances, comparable to the de Broglie wavelength, is described by two basic equations, the Schrödinger equation and the Klein-Gordon equation. For someone who is not familiar with quantum mechanics, the form of these equations will seem incomprehensible, but it is not so complicated. A trick was used here consists in the use of the so-called eigenvalues of operators. The operator is something that acts on a function. It could be differentiation, multiplication, etc. If we are acting the operator upon a function, and as a result we get the same function multiplied by some constant value, then this constant value is called the eigenvalue of the operator. Now let's see how this operator, IHD by dt, affects the wave function. We simply differentiate the wave function over time. And as you can see, we go through the points one by one, and finally get the value of if c. That is, the eigenvalue of this operator is the total energy E. While treating the individual parts of both equations in the same way, we get the following equations for the Schrödinger and Klein-Gordon equations, and after dividing by the wave function, we get a non-relativistic equation for the Schrödinger equation for total energy, which is equal to the sum of non-relativistic kinetic energy, the energy written in this way is ordinary mv squared by 2, and of the potential energy. And for the Klein-Gordon equation, we obtain a relativistic relationship between total energy, the rest mass, and the relativistic momentum. So you can see that the Schrödinger equation is an equation describing non-relativistic problems, and the Klein-Gordon equation describes relativistic problems. We can invert our reasoning, and from simple equations for energy, with the knowledge of the wave function, we can find the shape of the operators, giving such eigenfunctions, and as a result we get both the Schrödinger and Klein-Gordon equations. Oh, now the physical description became to be complicated. However, mathematics is a very capacious tool, and even if we assumed that just the dwarfs are responsible for all the properties of bodies and waves, and the values of physical constants depend on what colors they clothes have, and whether they are more or less satisfied, or whether they are clean or dirty, then we would most probably find an appropriate mathematical model that would be able to describe it, and the obtained results could be confirmed experimentally. From the history of development of science, for example, from the history of the formulation and development of epicycle theories, it can be seen that the excessive complication of the model may suggest that at some point the theoretical model began to set away from reality, and we should look at the problem from a greater distance and revise the approaches taken so far, even if the model in its current shape was still working properly, because further wading into the model development will result in an exponential increase in complication, as we already see in the standard model, for example. The current concept of motion, where there are bodies and waves that move according to different principles, but at the same time bodies have wave properties and waves have properties of bodies, may suggest that bodies and waves are two aspects of the same phenomenon that we simply observe differently. Similarly to a square and a circle, figures which when considered on a plane have separate properties, but already considered in the three-dimensional space may turn out to be two projections of the same cylinder. I have shown this time of effects in previous presentations. For example, what are time and space, where the time dimension and space dimensions are simply identical directions in E4. Only these directions are perceived differently by us. So, let's look for a common denominator for the motion of bodies and waves. Particles, that is waves and more. According to my model of the four-dimensional Euclidean reality, which I describe in the presentation on my YouTube channel, all particles are waves that move in E4. For waves traveling on rectilinear trajectories, it is motion with the absolute velocity v equals 1. At this speed, the path traveled by the wave in E4 is equal to the time elapsed in the system of this particle. More accurate information can be found in the presentations What are Time and Space? Time-Space Theory of Relativity Simple Explanation, or in my publication in the International Journal of Theoretical and Mathematical Physics. In my 2017 paper, I showed that a particle in E4 can be represented in a coordinate system bound with a wave, i.e. moving in E4 with absolute velocity v equals 1, as a wave in E4 described by the complex function, whereas it is the path traveled by the wave in E4. Since, as I said before, the distance traveled in E4 is the time measured by the wave body's clock, so for the observed body we can write that the wave is described by the equation. The complex notation was used here, in which the proper time of the observed body, that is the direction along which the wave travels in E4, is marked as imaginary. However, actually both the direction along which the wave travels and the other three directions of E4 are identical. Since the direction along which the wave travels is perceived by the wave differently than other directions, i.e. as time, then the imaginary number is used only to separate the effects being for us the result of the time flow, motion in E4 along the trajectory, marked here as imaginary, from the effects of observation carried out along the other three directions, marked here as real. This does not mean that the E4 space is complex, because the imaginary value relates to the direction of the wave motion in E4, and these directions are generally different for different waves. The use of complex numbers to separate time-dependent effects from time-independent effects is nothing new. This is used, for example, in calculating electrical seconds, where the impedance is described by a complex number. I would like to emphasize here that the phenomena occurring in electrical seconds are described by Maxwell's equations, and these, as we know, are the first relativistic equations in history. The magnetic field is a relativistic effect resulting from the motion of electrons. Then, the use of complex calculus in relation to the problems of the theory of relativity is perfectly justified. It should be noted that the transition from the description of the wave in E4 to the description in Minkowski space causes that the wave equation takes the form of the wave function, which I talked about a moment ago in the context of the Schrödinger and Klein-Gordon equations. You can find the derivation of this formula in an article in the International Journal of Theoretical and Mathematical Physics. Now, if we write our wave equation like this, it can be seen that our wave is not an ordinary wave, but is a combination of two waves. A transverse wave describing vibrations in a plane perpendicular to the direction of wave motion, and longitudinal wave, defining vibrations along the direction of wave motion in E4. The above formulas concern the description of a wave in a system related to the wave, i.e. moving with the absolute velocity of v equals 1 in relation to E4. If we now want to describe the wave in relation to E4, then in the above formulas we must take into account the motion of this wave in E4, i.e. the formula describing the body wave takes the form. A wave with such a shape and amplitude defined by this formula is presented in the 3D animation. More precisely, this animation and all subsequent ones can be viewed on the math3D.org website. Links to the animation will appear next to the animations. So our wave is not basically a wave, but rather a vortex whose projections onto the three-dimensional space xyz and onto the x t', y t', z t' planes have the shape of ordinary oscillations. The 3D animation shows how the wave behaves in xy t' space, where t' is the z-axis in the animation. It can now be seen that the complex form of the wave function known from quantum mechanics is simply due to the fact that the particle is formed by a superposition of longitudinal and transverse vibrations. We will assume here without proof that transverse vibrations are responsible for electrical interactions and longitudinal vibrations for magnetic ones. In a moment, when discussing the quantum energy, we will see that this assumption fits perfectly with the nature of the quantum. More about the structure of the particle and the consequences of such description as properties like spin, probability, uncertainty principle, particle and field, etc. soon in the next presentation or in the publication in IJT-MP. For now, we will focus on the properties that make particles observe each other in a particular way, and this way of observing is in turn responsible for our interpretation of particle motion. So we already have a predefined shape of the particle as a wave. However, the waves has no eyes. They communicate by sending and receiving signals. And only these signals inform the waves, and consequently us made of such waves, about the existence of the environment, about movements, and about the shape of reality. However, by observing the surroundings, we perceive enormous amounts of information, which on the one hand create a picture of the reality, but on the other hand gives us its false image distorted by the observation process. This picture, as I have already shown on the example of Ptolemy's geocentric model, may lead to the construction of erroneous models of reality. How do bodies wave communicate? Everyone knows how. Bodies send photons that propagate at the speed of light and that have no mass. A sentence taken out of the catechism. It describes everything but explains nothing. So, let's take a look at the structure of a particle and try to see what such a photon could be. How is such a photon sent by and received by a particle wave? First, a particle written this way, it has all the points on its reach, all the way to infinity, that vibrating in the same phase. If the particles are moving in E4 with the absolute velocity equal to 1, maybe also the information regarding the wave phase also travels along the particle reach at the velocity of 1. In this case, the particle equation can be modified and written as follows. For receiving signals in one direction, and for sending signals in the opposite direction. Both of these waves have a vibration phase velocity along the reach of the wave, and the phase velocity is equal to 1. Thus, the basic element of the particle will consist of two waves with opposite phase velocities along the ridges of these waves. The points of the fixed phases are marked with dots in the animation. We will limit ourselves in this presentation to the consideration of one wave. More in the next presentation on particle structure. Please come soon. Now, if a disturbance appears on the wave's ridge, It is transferred along the wave's reach with an absolute speed of 1, and simultaneously the wave travels along its direction of motion at an absolute speed of 1. In E4, the disturbance moves with the absolute speed equal to square root of 2. However, from the point of view of the wave, for which the path in E4 is interpreted as time, the speed of disturbance is equal to 1. It is an absolute value and does not depend on the direction of the wave's motion, which can be seen in the presented animations. Note that if we assume that the transverse vibrations are responsible for the electrical interactions and the longitudinal vibrations for the magnetic ones, then our disturbance will be exactly an electromagnetic wave. This is not visible in the animations because the disturbance is represented here as a point. However, in practice, the frequency of the quantum is much lower than the frequency of the de Broglie wave, so this disturbance will extend over many periods of the wave body and will have the effect of changing the EM field. Additionally, a disturbance defined in this way is not a free particle, but rather a parasitic particle that exists on another particle as its disturbance. Hence, most likely follows the observed lack of quantum mass. It is not fully mathematically described yet, but it is a logical conclusion that creates a coherent concept of both particles and quanta. So we can now answer the question: particles or waves? Each particle is a wave propagating in the Euclidean four-dimensional space with an absolute velocity equal to 1 for inertial motions. A quantum defined as a particle disturbance propagates in the system of each particle wave along its reach with an absolute velocity in the particle system equal to 1. It is observed as an electromagnetic wave and has no mass of its own. The quantum speed in relation to E4 equals to square root of 2. One of the forms of particle interaction, but not the only one, is the exchange of quantum disturbances. Now, when we know how particles exchange signals, we can determine how particles observe their surroundings. In turn, the knowledge of the method of mutual observation will allow to define the relative motion of particles' waves. The topic was presented in the presentations: why the speed of light is constant and what are time and space. But just in case, I will briefly remind you the basic points of this reasoning. Error third: motion concept. The particles exist in the four-dimensional Euclidean space. All four dimensions of the E4 are identical. However, the fact that we move in E4 in a certain direction and receive and send information along three directions perpendicular to the directions of our movement in E4 wave ridges causes that we perceive these directions in different ways. The direction of motion in E4 is interpreted as the time axis of our coordinate system, while three mutually perpendicular directions perpendicular to the direction of motion in E4 are the space dimensions. The observation by the exchange of disturbances, quanta, consists in the fact that the disturbance travels along the reach of the sending wave and then goes to the reach of the receiving wave, and there it also travels with the absolute speed equal to 1 in the receiving wave coordinate system. Thus, both waves, regardless of their direction of motion, observe that the disturbances are moving at the speed of 1. The sum of the paths traveled by the disturbance along the wave trajectory, interpreted by these waves as the flow of time, is equal to the sum of the paths traveled by the disturbance along the ridges of both waves, the sending and the receiving waves, i.e. the speed of propagation of the interactions is always equal to 1. Since the observer does not know what the actual trajectory of the disturbance is, in the case of a quantum, we are only able to register the quantum emission point and the quantum receiving point. And we see that the quanta always propagate with a constant velocity of 1, so we have the impression that the spatial direction is perpendicular to the trajectory of the body sending the signal. More on this in the presentation why the speed of light is constant. In fact, the condition of perpendicularity of the direction interpreted as a space dimension is met only when the trajectories of bodies that observe each other have a common origin. More on this can be found in the previously cited publications and presentations. With such an interpretation of space dimensions, it turns out that the relative velocity of bodies is equal to the sine of the angle between the trajectories of mutually observing waves. So we actually have three types of moves. Absolute motions. 1. Motion of wave bodies along the trajectory in E4. This is an absolute motion with velocity v equals 1, independent of the direction of wave propagation. We interpret this motion as the flow of time. 2. Motion of a disturbance, quantum. It is also an absolute motion, always along the direction perpendicular to the trajectory of the sending or receiving body, i.e. along the reach of the wave body. This is the motion with absolute speed v equals 1, measured in the particle wave system sending or receiving the signal. In relation to E4, this velocity is a combination of the absolute velocity of the particle wave in E4 with the absolute velocity of the disturbance motion along the reach of the wave particle, which gives the absolute velocity v equals square root of 2. Relative motions. 3. Relative velocity of wave bodies has nothing to do with the absolute motion of wave bodies or quanta in E4, and it is only a measure of the angle between the trajectories along which the wave bodies propagate in E4. In this case, v equals sinus v. In the current model of space-time, the two velocities mentioned in points 2 and 3, which are completely separate and mutually independent phenomena, are treated as identical relative velocity, which caused complications. Thus, the mistake in modern physics is the use of the same concept of motion both for the relative motion of bodies resulting from the inclination of the body's trajectories and for the motion of disturbances, which is absolute and does not depend on the angle of the trajectory in relation to the trajectories of other bodies on which the bodies move. Treating these two completely separate phenomena with the help of the same concept of motion as we apply to the description of the motions of the bodies surrounding us, resulted in the adoption of the naive and even nonsensical assumption of Fitzgerald-Lorentz on shortening bodies in motion, which in fact has not been confirmed experimentally, despite of approximately 150 years since the formulation of this thesis. The shortening of Fitzgerald-Lorentz was the most primitive explanation of the much more complicated phenomenon of mutual observation and motion of bodies and the wave structure of bodies, something that was not known to Lorentz and Fitzgerald as well as Einstein at the time of formulating the theory of relativity. As a result, both theory of relativity and quantum mechanics are overly complicated not because of the actual complication of reality, but as a result of incorrect treatment of motion, not as a motion can be represented in E4, but as we see this motion by observing our surroundings, where light, celestial bodies and objects, they move around us as if these motions they were identical motions. We distinguished the motion of celestial bodies from the motion of objects on the Earth relatively recently, which resulted in the rejection of the Ptolemy's model. But we still do not distinguish the motion of EM waves from the relative motion of bodies, which makes the theory of relativity and quantum mechanics similarly complex and incomprehensible as until recently the theory of epicycles. So, if today you can imagine a discussion of an advocate of theory of Copernicus or Galileo with the Holy Inquisition 300–400 years ago, Then you will understand my today's problems with reviewers and why, instead of publishing my theories in reputable journals, I publish presentations on YouTube. On the other hand, it is YouTube with its multimedia tools that offers much wider presentations possibilities than typical journals. To sum up, when considering the concept of motions, the two errors were made consisting in treating as identical the two different types of motions. The first error of Ptolemy consisted in not distinguishing between the motions of the bodies around us and the motions of celestial bodies, and, consequently, using the same reference frame to describe them. The second error of Lorentz and Fitzgerald, adopted by Einstein, consisted in not distinguishing absolute motions from the relative ones, and, consequently, rejecting the hypothesis of the existence of an absolute reference frame. The attempt to treat the separate motions with an identical tool led to breakneck mathematical tricks, which resulted in a complicated and incomprehensible model of reality. Appendix. What did the Michelson-Morley experiment actually prove? In the Michelson-Morley experiment, it was assumed that the motion of light relative to the ether and the motion of bodies in the ether are identical phenomena, such as the motion of a ship and waves on the water. In that case, changing the direction of motion of the interferometer should cause the speed of EM waves to add to or subtract from the speed of the interferometer. Meanwhile, according to the proposed approach, the speed of the interferometer is absolute speed, just as the speed of signals in the interferometer is absolute speed and results from the absolute motion of the interferometer system and signals in E4. This motion is independent on the rotation of the interferometer in E4. Meanwhile, the relative motion that we observe depends only on the change of the angle of motion of bodies in E4. So, by changing the speed of the interferometer, we only turned it in E4, which could not change its indications. It was a mistake of Michelson-Morley to identify the motion of EM waves with the relative motion of bodies, while, as I have already shown, these are the separate phenomena defining something completely different, but similarly named, as, for example, the Adam's apple, which can be related to anatomy or to fruits. No wonder that the experimental finding of relationships between similarly defined but completely different phenomena did not bring any results. Thank you, and I invite you to the next presentations, coming soon.